Hi and good day to all students. So in this chapter, we are going to talk about dislocation in material. So in general, we can define dislocation as a line imperfection in otherwise a perfect crystal. That we're going to talk more about that later. Right, so let's start our video with what do you know about dislocation? Yeah. So in crystallography, dislocation is the displacement of a part of a crystal lattice structure. Yeah. So we can say that dislocation is a defect in crystal structure where the atoms misalign. And we know that ideal crystals, perfect crystals, are defect-free, and not so ideal ones or real crystal will have imperfection. So defect, why is defect in crystallography is important? Because it will influence the material property. Yeah. So ideal crystal is a lattice and the motif. A lattice is the 3D periodic arrangement of point, and the motif is the atom or group of atoms that associated with the lattice point. So ideal crystal, it will have defect. On the other hand, real crystal are defect-free. Yeah. So how can we classify defect? So we can classify defect as the point defect. We have a point defect such as a vacancy, interstitial. We have a zero-dimensional or point defect such as vacancy or interstitial, and also we have a line defect. That is a dislocation. Line defect also known as a one-dimensional or point defect. And also we have a two-dimensional or surface defect, such as grand boundary, twin boundary, and also a stacking fault. So why does ceramic is more brittle, while on the other hand, metals tend to be ductile? Why? So if we look here, we can compare between, we can see differences between metals and also ceramic. So we know that metals tend to be ductile and it has a high number of dislocation. Yeah. So if we look here, we look at the figure here, we can see we have an electron cloud and we have an ion core here. So a dislocation motion is easier in metals because we have a non-directional bonding and also we have a closed back direction for slip. For example, here we can see that the ion core is surrounded by free electron, and due to non-directional bonding, so the metal, it can slip in any direction. And how about ceramic? Ceramic, as we know, it is a hard and brittle, and it will exhibit a limited plastic deformation. And dislocation are quite rare in ceramic, and fracture are more common. Why? Why is that? Because in ceramic, it is bonded by covalent or ionic bonding. In terms of this dislocation in ceramic, the atoms or the ions, it cannot easily move. A slip will not occur, or it doesn't occur, and dislocation remains stationary because we need a motion is hard because we need to avoid plus and negative neighbors, and we have a non-directional bonding in ionic ceramic. So it is quite difficult for dislocation to happen due to ionic or covalent bonding. So in covalent bonding, it is directional. For example, we have carbon and oxygen bonding, and the movement will requires breaking the bond. And on the other hand, we also have ionic bonding in ceramic, where the electrons will transfer. For example, sodium chloride, where the electrons will transfer, and it involves a transfer of electrons, creating a positive and negative ion. The ion will bond through a Coulombic attraction force between opposite charge. Yeah. So the hardness and brittleness are extremely high in ceramic, but still plastic deformation, still it occurs in a tiny amount in ceramic, but it is far less than the metal, and usually happen near the melting point. Yeah. And we can say that dislocation in ceramic is quite rare, or also we can say it as virtually non-existent, and it is difficult to move atoms due to the bond nature. And moving the positive ion, as we can see here, if we move the positive ion near another positive ion, it will generate electrostatic repulsion, making dislocation is nearly impossible. And how about non-crystalline ceramic? Yeah. So non-crystalline ceramic or amorphous ceramic is a type of ceramic where the atoms are arranged randomly, not in a set pattern. It is a non-crystalline ceramic, meaning that it has like a regular atomic structure. In terms of structure, it is similar to glass without regular atomic order. And in terms of deformation, traditional mechanism like dislocation don't apply due to the structure. And we have some examples of non-crystalline ceramic, such as silica glass. Also, we have soda lime glass, and also we have borosilicate glass. Right, so we already know that materials may experience two kinds of deformation, that is plastic and elastic. Yeah. So deformation of material is due to the changes of due to the mechanical forces. And we have elastic deformation, where the materials will return to original shape and shape to original size and shape after the loading is removed. And also we have plastic deformation, where the mechanical loading will cause a permanent size and shape change to that particular material. Yeah. So we know that plastic deformation is permanent at the microscopic scale. It corresponds to the overall or net movement of large number of atoms in response to the applied stress. In a crystalline solid, plastic deformation usually involves the motion of a dislocation, where the interatomic bonds will rupture and reforming. So here we can see, like what I have just mentioned just now, we have two types of deformation. We have plastic and elastic. How do we differentiate them? For elastic deformation, it is a temporary shape change that is self-reversing, as we can see in the graph here, after the force is removed. And in plastic deformation, it is the permanent distortion that occurs when a material is subjected to stress. So what can we expect during a plastic deformation? In plastic deformation, we can see a net movement of large number of atoms, and the bonding will be ruptured, and it will involve the motion of a dislocation. And in this slide, I show you two types of defect that we have here. We have a line defect, 1D or line defect, and also we have a 2D or planar defect. Okay, we take a look first at this 1D or line defect. In this type of defect, it involves many atoms in length. It is called dislocation. It is a quite commonly found in crystalline materials. This type of line defect is very important because it will affect or determine the material's mechanical strength. Yeah, and for line defect, we have two types. We have an edge dislocation. That is a type of a line defect where we have an extra half plane of atoms that exist, like what you can see in the figure here. And also we have a screw dislocation. That is a type of a line defect in a crystal where the crystal planes will spiral around a dislocation line. Yeah, and now we take a look at the 2D or planar defect. That is an interface between adjacent grain in a lattice, like what we can see here. So we can see in the figure here, we know that the atoms in a grain boundary is not in the perfect crystalline arrangement, and any disruption in stacking sequence, it can lead to stacking fault and also a twin region. Right, so if we compare between stacking fault and a twin region, stacking fault, we can say there's a change in atomic layers that makes the materials more bendable. Yeah, so it is a break in the normal sequence of atomic layers, and the effect of a stacking fault, it will lowers the stacking fault energy, and at the same time it will increase the ductility. And below here we have a twin region. Twin region is a mirror-like, as you can see in the figure here. Twin region is a mirror-like areas in crystals that make the materials stronger. Yeah. So a twin region is a mirror-like reflection of atoms across a plane, and as a result of a twin region, it can enhance the material strength, and at the same time, it may impact the ductility of that particular materials. All right, so in this slide, we have a variation of a defect. We have a point defect, extended defect, vacancy, interstitial defect, and also we have a substitutional defect. Right, so we look at the point defect here. So point defect can be described as a small error or small in imperfections such as vacancy at one or few spots in a crystal. And then we have an extended defect that we can describe as a larger error across many atoms in a crystal, like a dislocation. So in extended defect, it may involve several atoms or ions that occur over a finite volume of the crystalline materials. For example, like I have mentioned just now, we have a dislocation, and also we have a stacking fault and so on. And if we look at vacancy here, we can describe it as a missing atom in a crystal structure. And then we have an interstitial defect that is an extra atom squeezed or located in the wrong location or in the wrong spot. And then we have a substitutional defect that we can describe as an atom that replaced by a different kind of atom. Dislocation will move on the specific slip plane based on the crystal structure. We know that FCC has a 12 slip system, and it is the most ductile. And also we have a BCC. It has a 48 slip system, and HCP, it has a 12 slip system. So under tension, some parts may still shear. Plastic deformation will occur from atomic planes shearing due to resolve shear stress. Yeah. So dislocation, it will move with shear stress. Tensile stress, it can create shear stress in some orientation that we call as a resolve shear stress. Resolve shear stress varies with the stress applied and also the orientation of the slip plane and direction. And slip will happen when this shear stress exceed the critical level. So in a single crystal, now we talk about a slip in a single crystal. We can define slip as part of a crystal that slides over another along a slip plane in a certain direction. Yeah. So shear stress is needed for slip to occur. We need the shear stress for a slip to occur on the slip plane and direction. So for example, if we're pulling a bar, it doesn't always cause slip in the pull direction, and only some of the stress will contribute to slip. So it must be calculated specifically. Yeah. So slip occurs first in slip system oriented close to lambda equals to 45 degree with respect to the applied stress. So slip occurs first in slip system oriented close to theta equals to lambda equals to 45 degree with respect to the applied stress. And here we have a Schmid law. That is the relationship between shear stress, the applied stress, and the orientation of the slip system. So this is the equation of Schmid law. We have a tau equivalent to sigma cos lambda cos theta. And also we have a critical resolved shear stress that we can define as the shear stress required to cause a dislocation to move and cause a slip.